Okay, yeah, please. I hear we have people on an office tour right now, and we have to bring them back. It's crazy stuff going on. Cool, I'll just start with a little bit of preamble. Thanks a lot for coming out. You're at PlanGrid if you haven't been here before. I think our offices are really nice, so it's always cool to bring in new people and to get to meet the team. The goal for this talk today is to be like in 25 minutes, and I also want to get you back into meeting people and chatting. But I also wanted to have a piece of content that's kind of interesting to a wide audience. So we're going to talk a little bit about API development, specifically around our web and mobile products at PlanGrid, where we have some specific requirements that I'm going to go into. But I first want to introduce myself real quick. My name is Benji Entz. I've been at PlanGrid for a little bit, almost 2.5 years now. I started out on the iOS team originally just as an engineer, then became an engineering manager a while ago. Back when I was writing a lot of code, I also worked a little bit on open source. So next to the PlanGrid logo, you can see this orange icon. This is from an open source library called ReSwift, and that is a Redux implementation for iOS in Swift. So I don't know if we have web developers in here that have worked with Redux before. Yes? Raise hands, don't be shy. Cool. If you ever work on iOS, you can use the same patterns using this library. But these days I write a lot less code, and the topic today is not going to be about mobile, it's going to be about API development. So what I want to talk about is how we develop APIs at PlanGrid. We actually have some interesting patterns that have evolved over the last few years. And part of that is moving beyond what is considered RESTful best practices. So most people here that are familiar with API development, you're probably writing RESTful APIs in some form. And we have started out that way, but we really noticed that our web and API clients have very different needs, and none of them are perfectly suited by standard REST. So I'm going to go into that a little bit. Oh, the clicker is not working well. Sad. So I'll just always walk back and forth between the laptop. So usually I don't do a lot of memes, but I did some research for this talk, and I came across this one that was very, very suitable. This kind of plays with the idea of the sometimes dogmatic approach that we take to adopting a certain standard just because everyone uses it. And the goal of this talk is to talk a little bit about how we evaluate a certain technique, even though it's a best practice, and see if it is actually applicable to the problems at hand. But I first want to go into some history, back to the year 2000 when REST was actually introduced. This came out of a paper, so it's actually an academic concept, and it was back in a time when a lot of the internet was actually driven by academia and not by big corporations. And the person that wrote the paper that introduced representational state transfer was Roy Fielding. And the paper was called, or his PhD thesis was called Architectural Styles and the Design of Network-Based Software Architectures. And Roy Fielding was actually one of the authors who worked a lot on the HTTP standard. And so when he was thinking about how APIs would be designed for the web, he noticed that a lot of the API protocols could actually be built on top of HTTP standards, and that would make for a really good API pattern. He introduced a lot of concepts, and most of them were new back then, because 2000, if you think about it, the internet was a lot of Flash applications, it was Java applets. There wasn't really the concept of like a client-side app talking to a server through a very dedicated interface. There were like remote procedure calls. It was kind of the wild west of API development. And so a lot of the concepts introduced are very common across various API standards today, but some of them are very specific. The first one was a separation of client and server. That was one of the main principles that he was pointing out. And the idea was to have a client, there was a totally separate code base from the backend that stores data, and the client being only concerned with rendering views for a user, and the backend being only concerned with storing information and manipulating information, and putting this strict interface between the two. So that was one of the constraints he introduced. Another one was that these APIs should be stateless, and this was a response to the anticipation that a lot of people would use the internet going forward, and that you would have to horizontally scale your applications, and not having sessions persist between a client and a server made scalability a lot easier. But these two constraints are actually present in a lot of alternatives to API design that are not RESTful. The most interesting one is the last one, it's uniform interface. And what that described is a standard that is applied to all different kind of APIs that makes them self-descriptive, that makes them traversable, that makes APIs very similar to websites, where you browse a route You can see elements, you can see which entities are available, you can see which operations are available. If other entities are referenced, you can follow along the path of the API. So the core idea was really the API could be similar to a website, which is really helps with discoverability. And I want to go into this last one a bit, because that's the one that most RESTful APIs kind of violate in some form. But he described as the core tenets of this uniform interface constraint as being the identification of resources, the manipulation of resources through representations, self-descriptive messages, and hypermedia as the engine of application state. And this last one talks a lot about this navigation of a RESTful API. So if you really follow these principles, again, you can look at an API and you can almost immediately see all the entities and operations that are available without reading any documentation. So this was a lot about standardization and discoverability. And I think it's one of the main drivers behind what we know as the API economy, because it made it really easy to adopt third-party APIs without reading a lot of documentation. If you've seen 2 or 3 RESTful APIs, integrating another one is very, very simple. So it has huge benefit for public APIs. But he also, in this paper, anticipated some of the trade-offs that I want to talk about today. And he said the trade-off, though, is that a uniform interface degrades efficiency, optimizing for the common case of the web, but resulting in an interface that is not optimal for other forms of architectural interaction. And this is the general trade-off. If you say I'm building something that's very generic and works for a lot of use cases, you're trading off optimizing for the specific use case at hand. So I want to talk about that a little bit in the context of APIs at PlanGrid. A little bit more history about PlanGrid itself, because you might not be familiar with us. For this audience of engineers, designers, people that build software, I like to talk about that we're building developer tools for construction. We're essentially building software that helps the execution phase of a building, everything that happens after the spec was written. So you can really take these analogies from software, where typically a product owner will write a spec, an engineering team will execute on that. In construction, the architect is the person writing the spec. And the people that are on the job site, that you can see on this picture, are the people actually building the building. And they need a lot of tools to do that. In the past, this was based on paper. What we are working on is a mobile-first application that you take onto the job site, and you can see all the construction documents, you can see the specs, you can see when changes happen, you can communicate status, you can track problems. So it's somewhat between GitHub and Jira for the construction industry. And it's better than Jira, if you don't like it. Cool. So that's enough intro. You can talk to more people here if you want to learn more. Today I want to talk about APIs. And we have kind of 4 categories of APIs at PlanGrid. The first ones I'm going to focus on, these are what we call our private web API and our private mobile API. And these are only used by the clients that we ship, so our web client and our mobile clients. We also have a public API, and I'm going to touch on that briefly. That's the one that our customers and third-party integrators use to customize PlanGrid or to integrate PlanGrid into other systems. And lastly, we have inter-service APIs. At PlanGrid, at our size, we have our backend is no longer just one app. It actually consists of multiple apps that communicate with each other. And they also use a lot of APIs, but that's a whole nother topic that I'm going to skip over today. So I'm going to focus a lot on the first 2 and talk briefly about public APIs as well. So let's start with the web component. So like many applications out there, what we have is a highly interactive application, and it's not really a website in the sense of what websites looked like in the year 2000 when REST was introduced. Here's an example of a part of the app. You can see what we call a sheet viewer, which allows you to see blueprints and to interact with blueprints. You can draw markups on sheets. You can create tasks and attach them to a blueprint. You can tap onto hyperlinks. So this is a highly interactive application. And the point I'm getting to is that web development these days is very similar to building native clients for Windows or for mobile devices, in that it is an interactive application and no longer a website. You typically have a JavaScript client running in the browser runtime that is acting a very similar way as a regular app does. And that creates some mismatches between the way REST was designed and our application works. What I showed here is I expanded the developer console, and you can see a bunch of requests that we're making. And for this page to load, there are actually 4 API requests that have to happen. I've got them on the next slide. I won't go into all these concepts in detail, but we have to fetch sheets, we have to fetch annotations, which are the squiggles that you can see on the plan, on the blueprint. We have to fetch a list of users for checking permissions, for being able to assign things to users. And we fetch a thing called stamp defaults, which is something for our progress and issue tracking tool. But the point is we have to fetch a lot of data to render a single page. So it's no longer a static web application where I can hit one endpoint and I get all the data I need. Instead, I have a client application that runs and collects data from very different resources. And in engineering, we sometimes use an analogy where we call this an impedance mismatch. And I did a quick research, and I found enough people that have the same question. So how do we overcome the impedance mismatch between a front-end client's need and REST principles? Because our need is we have a page, we have a view that requires some data to function, but we're working with a backend that thinks in terms of individual entities and resources. And that requires us to make a lot of separate requests to gather all this data and to join it on the client side, which is a lot of API overhead, a lot of API calls, and also a lot of work for the engineer to think about all these endpoints, find them, and to join all the data together. So how can we do better than that? What we really want is that web APIs provide the data in a shape that is required by that view. So really we want a one endpoint where you can go and say, give me all the data that I need to render the sheet viewer, or give me all the data that I need to render this newsfeed. And I don't want to go to 50 different places to collect this data. But it's fundamentally incompatible with a really RESTful API, because RESTful APIs think in terms of resources. And something like this would not work, where I say sheet viewer for a sheet. This is not a resource. It is a very specific endpoint tied to a view. So we would not want to do that. But as I mentioned, a lot of people have run into this, and so luckily, someone has created a tool to solve this specific problem, and that is GraphQL. Who here has heard about GraphQL before? Okay, it's become very popular in the last 2 years, I think. So what GraphQL is that they call themselves a query language for your API, which I think is a pretty concise description. And the idea is to solve exactly this problem that I just described. We have a client application that knows exactly which data it needs, and we want to avoid to find all the different endpoints based on resources to collect this. And instead, we want to say, here's all the resources you need. Backend, go fetch all these different resources and provide them in one request. I won't go too deep into this. All the concepts today are going to touch on a very high level because they're all could be talks entirely of themselves. But here's just so you can understand the concept if you haven't seen it before, what a GraphQL query looks like. It's essentially very similar to a database query. The syntax is a little bit different. In this specific example, what is interesting is that this is actually based on two real-world APIs, and one is the Eventbrite API, and the other one is an API called Dark Sky, which provides weather information. And what the author of this blog post wanted to demonstrate is that you can combine two totally separate APIs in one single GraphQL query, and you can pretend to the client that you can fetch all this data with a single request. Whereas in the backend, you can do all these different calls to the different resources and gather that data together. So what does this look like? I won't go into this in too much detail, but the idea is that you can put GraphQL on top of your existing infrastructure without rewriting everything. So the whole stack was designed such that there are a lot of customization hooks. Essentially, what you do is you tell GraphQL through various configurations where which kind of entity can be found in your backend systems. So you might have multiple databases. You can tell GraphQL users are found in this database. Content for these users, whatever is on their timeline, is found in this other database. And GraphQL will automatically query the right database to find the content. But I don't want to go too much into GraphQL. The main point I'm trying to get across is that REST, the way it works, the way it was designed does really work perfectly for the use cases that we have for the web. The benefits that we get from using GraphQL is we have a single API request to get all data instead of having many API requests where we have to join the data together. We have a front end that can evolve independently from the back end. So if you're adding a new view to your app, you don't have to tell a backend engineer to write a new endpoint to serve specifically that case. You can just have the front end decide which data it needs and have that evolve separately. And the last one is you can avoid a lot of problems around API versioning. I won't go into this one in detail because that's another whole topic, but if you look into GraphQL, you'll see some interesting concepts around versioning there. But the main point, again, is we have a mismatch between what web applications do today and what REST was designed for, and there's better technology out there that we can investigate. At PlanGrid so far, we had a Hack Week project that tried to integrate GraphQL and was actually pretty successful. But for various reasons, we didn't double down on that. It was almost a year ago, and GraphQL was still pretty immature. So we're not using any GraphQL today, but it's definitely something you're looking out for. And I think it's going to stay top of mind, and we're probably going to implement something like that sometime down the road, because it really provides a lot of benefits. Cool. That's all I have for the mobile side. for the website. And this really applies to almost all web applications out there. It's not specifically tied to PlanGrid. The one thing that is a little bit more special for PlanGrid is how our mobile APIs work. And that is because our mobile APIs have to work together with offline compatible apps. So I told you about more or less what our product does. People go on a construction site, they take a mobile device, they look at construction data. What's really important is that the app works the same way, independent of the network connection. Whether it's flaky, it's totally gone. Whether you go without internet for multiple hours, we want that people are able to work. And this is going to stay like that for many, many years. Even in an office like this, if you have an app that doesn't work entirely offline, you run into issues. We have a code review tool that does that, that some teams are using. And even when you're sitting at your desktop, sometimes you have spurious network connection. So it's really important to not block people because of their network connectivity. And that has downstream implications on how these APIs have to work. And one of the big ones is that for all of our mobile apps, as soon as they have network connectivity, we fetch all the data that a server has that has changed since the last time we were able to fetch data, and we store that in our local database. So every mobile app has a copy of all the data that's relevant to this user at any point in time and can always operate on that local data instead of relying on API calls. So essentially, the problem we need to solve is we have an ongoing data replication problem. And if you're a backend developer who has maybe worked with databases that are spread across multiple data centers, this is actually a similar problem. You can imagine abstractly every mobile device being a data center with its own little database, and it having to be synced constantly with the global database that we're hosting somewhere on AWS that is central for all users. And because that is also, it's a fairly common problem, a lot of apps actually try to work entirely offline. And so this is also somewhat a problem that has been solved in a few different ways. There are different tools out there. You might have heard about CouchDB. Has anyone heard about CouchDB before? Yes. The other ones, there's some commercial ones. Cloud Firestore is very new. Realm has been around for a while, and I think we maybe even have someone from Realm in the building today. Then there's PouchDB, which is an alternative CouchDB. But what all these tools promise is they provide this idea of data replication for free. So instead of writing code to replicate data between a server and a client, the data replication happens as part of the product or tool that you're integrating. But the problem is that all these tools rely very heavily on having a per-user database model. So they work really well if you build an app where most of your data is user-specific, so a notes app or a reminder app, something like that. They're probably more complex examples. But they don't really support the use case that we have very well, where you have data that is shared between a lot of users on a project, but only some users are allowed to see some subset of the data, but all people are manipulating the same data. So we have to kind of do what we call a filtered replication, where we need a central database, we need the same view into all the data, but we only want to show some data to some users. And there's really no solution that works off the shelf for that, unfortunately. All of these, PouchDB has some rudimentary support for it, but it is really not supporting many of our use cases. So as of today, we still have to build this ourselves. So what this looks like conceptually is we have our backend services and our backend databases. For the biggest part, these are Postgres SQL databases. We still have a little bit of MongoDB. And so these global databases store all of PlanGrid users' data across all projects anywhere in the world. And then we have these mobile devices that have a SQLite database that is a snapshot, a copy of a snapshot in time when they had network connectivity for the last time. And then we have our API layer in the middle that has to synchronize between these two. And that has to apply a permission and visibility rules. So as I mentioned, not all data in PlanGrid is visible to all users. There's some pretty complex use cases that our customers want. One example is if there is a problem on a project that is tracked as an issue, similar to a GitHub issue, there are some cases where it's only visible to the person that it was assigned to, but not to anyone else. So when we replicate and when we try to figure out which data do we need to copy to all these mobile devices, we have to look at the permissions and we have to select the data accordingly. And we do that by writing manual code, and that manual code is behind sync endpoints. So we have a lot of endpoints for all of our different data types where we have, for example, annotations/sync. And the annotations/sync endpoint is responsible for providing all the markups. These are the things you saw on the sheet that people can draw that changed since the last time we synced successfully. So the pattern here is that we have some kind of token that a client can remember, and every time we sync, we pass up that token, and the server looks at the token, identifies which data changed since we synced the last time, and sends us down all of that data. And then we store all the data locally, and we can continue working with the mobile app without hitting the server again. Hope that makes sense. I know it's a very dense topic. But essentially what we're doing is we're implementing this database replication protocol in our own code, whereas really what we would want is it to be a real database replication protocol. So today we're still using something that looks a little bit like REST, but it has nothing, it really has no resemblance of the concept of synchronizing this state and pagination that you would typically do in a regular REST API. Instead, we're just trying to synchronize all these records from our database. So today we're still using something that looks very similar to REST, but actually we would be moving to something like Realm or CouchDB if it was working. So it's another use case where REST really doesn't fit our needs exactly. And then there's the last one that I didn't talk about. So far I talked about how we read data and how that is different for web and for mobile. But changing data in REST APIs is another interesting topic. So if you think about applications abstractly, they are a collection of states and operations on these states. But when you follow the history of REST, REST is really focused on state transfer, not on operation transfer. In fact, when you model an API following RESTful principles, there is no concept of an operation. There's only concept of updating state within an API request. But people at PlanGrid, our customers, and a lot of other applications too, really care about events. If something like this happens, user A assigned issue X to user B, then we maybe want to notify people. We maybe want to show this in a newsfeed. We maybe want to send an email. These kind of events, these semantic changes in the data are really important, and we need to keep track of them. And if we work with RESTful APIs where there's no concept of operations, then we end up with a situation where we actually have to reverse engineer this information out of the state changes that happened. So we have some initial state where we have an issue and there's no assignees, and now some client sends us a new state, and we have to see what changed between the previous state and now. And by diffing, we can identify that some assignees have changed, for example, or that an issue was opened or closed. But we have to write code for this, and errors can happen. And it gets really tricky if you have to diff state changes across multiple properties. And sometimes it can even be ambiguous to identify which operation exactly happened on an object if you only have its previous state and its current state. So there are a lot of issues here. There's also no way to add additional context to this change. For example, where did it happen? Maybe someone cares about the geographical location. The REST API just doesn't have the concept. It only has the concept of replacing the current state with a new state. And that's a big downside for applications like ours. And then there's the last part to this concept of data mutations in REST APIs. And that is that these mobile clients that I talked about that are operating on these local databases, they already think in terms of state changes more in terms of operations than in terms of state transfers. And that is because all the different changes that happen to your local data have to be tracked separately, and they cannot be lumped together into one state update. So the scenario here would be, I'm offline for 5 hours, and I added multiple fields of my object multiple times. I want to keep track of all these individual changes, such that when I next time have internet connectivity and I send this to the server, I get a full history of all the individual changes that happened. If I would follow a REST principle, I might just update all this in place and only send one state update, but then I would lose the entire context of the history of edit events that happened. And I also lose some control about being able to reject individual changes. So we actually do this where some operations are valid, some are invalid, and we are able to reject them individually because we keep track of all these changes separately. So our mobile clients already think in terms of operations, and a lot of the mobile code is actually implemented to keep track of operations and to not think about state changes. But there's again this mismatch between how the API works, because it's RESTful, and how our mobile clients think, so we have to translate on that layer. And that just adds some overhead. So between REST and the concept of operations, there's another smaller impedance mismatch. So it summarizes the kind of problems that we have working with RESTful APIs in these kind of applications. But I briefly want to talk about the public PlanGrid API. This is one you can actually see on developer.plangrid.com. We're hosting it for anyone who uses PlanGrid to interact with. And for this API, as I mentioned at the beginning, because it is public, following REST principles is actually really important. So while we're deviating internally and adopting something that works for our application, for the public API, we're going to stick with REST for a long time, because it's very important to adopt something that is self-documenting, that is a standard that is widely used, and that people are very familiar with. So internally, we're moving more away from REST in some ways, but externally we're not. So what does it all mean for PlanGrid APIs in future? I just want to summarize again the different kind of problems of REST in the context of our APIs that I talked about. There's a impedance mismatch between REST and a typical web application and how it reads data. And GraphQL is one of the solutions that came out of that problem. There is also an impedance mismatch between REST and the concept of data replication. As I said, ideally we just want a database technology that takes care of data replication. And we don't want to write fake, seemingly REST endpoints to emulate this, but today we have to. And then last one is the last one I talked about, the concept of operations being hard to model inside of REST. We just have these state transfers, and we have to reverse engineer operations out of these. So with all of that being concluded, what we're doing is we're still using an API that looks very similar to REST, but it's definitely moving away from some of these principles, specifically that uniform interface one that I talked about a lot in the beginning. And we do that as we see better approaches come up that work. And the core idea here is really to look at a tool and see what works and to not be scared to reinvent a wheel sometimes. So some of you might think it's really bad to move away from REST because that's just a widely adopted best practice. I have a very interesting blog post on this from codinghorror.com, and the title is "Don't Reinvent the Wheel Unless You Plan on Learning More About Wheels." And I think that's generally the mindset I have around these kind of things. You don't want to run off and just abandon a standard or best practice because you think you have a better idea, but if you have worked with the standard or best practice for like 2 years and you see some patterns emerge, and you have a mature engineering organization that can support it, then it can make sense to deviate from the standards to actually get the benefits of specializing for your particular needs of your application. And the way we do it is, again, we evaluate this on a case-by-case basis, and we make sure that it's supported by good internal documentation, like what is the best way to build APIs at PlanGrid if you're not following a widely adopted best practice. We want to build tooling. We want to have APIs that support developers in building synchronization the right way, so they don't have to do it over and over again, for example. And we need really good onboarding. If you do something non-standard, you just have to spend a little bit more time ramping people up. But in our experience, if people are going to stick around for a long time, these few weeks that it takes to on-ramp them onto some proprietary techniques is really valuable downstream. So that's most I have for today. I think I stayed within my time limit. I've linked to the slides. All of you are obviously smart people, so you know that a part of why you're here is because we have jobs, and you maybe need jobs in future. If that's the case, you can find jobs here, and you can talk to people. I've also linked to a bunch of resources at the end of the slides, so if you download the slides, there are all the blog posts that I talked about where you can learn more, because I went over a lot of topics today. And I'm also open for any questions. Thank you. Does anyone have questions? We have a microphone actually for this, so if you want to ask a question, don't be shy. If no one has questions, that's fine too. We have one.
Okay, so I just started doing back-end development on my own or with a team member. Sorry. Bad intro. So why only push the actual data? Why not just push changes? Like I added this, I added that, I removed that, and then in the back end it'll just like add everything up and be like, oh, this is the new states. This is what currently the file looks like for say.
Yeah, that's a great question, and it would be an absolutely valid pattern. The reason it's not done that way today is because you started out with a RESTful API. And the idea behind RESTful APIs is you always send the latest state. But as I mentioned, we're kind of moving away from that. And so when I started here, we were redoing the way that the iOS app specifically syncs data to the server. And the way I built it there was actually to have in mind just send these changes. We just haven't yet committed to that we actually want to do that on backend. And there's some potential there can be potential problems around that too, where it becomes harder to identify that your client has gotten out of sync with the server state because you're no longer sending a full copy. You could work around it by having something that's called like a version vector, which is like a version number, essentially, that compares to see if the client actually has the latest version that the server has, and only then the changes are applied. But yeah, conceptually, it makes a lot of sense. And if you build APIs, there are only two ways to sync. There's one, I send you all the state, or the other one is I send you operations or changes. But we're historically, because we started out with like the standard REST, we're still on the state-based model. Cool. Any more questions?
So keeping on that sync question, one thing I was wondering is sync conflicts, and you'd mentioned like version vectors. Is that the case, or are you clobbering?
So when it comes to sync conflicts, we're basically, in most cases, last writer wins today, which I'm saying off the record, just in case any very technically capable customers are listening. No, but essentially what we've noticed is we're definitely collaborating, but we're not really real-time collaborating on the same objects very often. It's really an edge case. It's not like a Google document where there's a good chance that people are actually editing the same paragraph of text. It's typically people are operating on the same sheet, but they each have their own markups that they're working on. That said, in an ideal world, we definitely want to implement something like a version vector to detect conflicts. And I think it's something we're definitely going to do downstream. But today, we're not doing that yet. And again, ideally, we would find a general pattern to do this, so we don't have to implement code, because it's generic across all record types. It should work exactly the same. So this is one of the challenges, like how do we build this out as an infrastructure layer instead of into these individual endpoints? It's something we're thinking through. Yeah.
Thank you.
So I think I know a lot of companies or teams that are talking about moving to GraphQL in general. Like it's something that we want to do, but I haven't seen a whole lot of like very concrete plans to transition to GraphQL without disrupting, their current use of their RESTful API. Like, do you have any ideas on like what are your thoughts on that? Like,
yeah, there were actually a few good blog posts about that. So technically, the way GraphQL works, it is intended again to adopt on an existing technology stack. So you can either build it on top of your existing databases, but you can even build it on top of existing REST endpoints. So you could take REST endpoints and map these to GraphQL entities. And you would have to write some additional code, but there are some examples that I found while doing some research where basically these existing REST endpoints were just cobbled together for the GraphQL layer. And when you were querying GraphQL, it was underneath the hood querying the original REST API and then joining the data together at that level. So depending on how your API is structured, that would be one way. Otherwise, I feel like in general for web, it's easier to gradually adopt this. You just start with, like the classical model is you take some page in your application that no one cares about, and you try to implement it in GraphQL. And if that works, then you move forward. That's how we did it for other platforms. We introduced like totally new design patterns. Yeah, I think and getting some organizational buy-in is another thing, obviously. But I do think there are quite a few companies that are moving forward with it. But okay, if there are no more questions, then I hope we can get back into this wonderful state of social interaction that I just disrupted with this. You can also ask me any questions in person, and thanks a lot for coming out. I hope you have a good time.